respect to Aboriginal and Torres Strait Islanders peoples here today. And just another reminder, if you are a regular here at the meetup, this pretty much should be already common sense and common knowledge, but community is dedicated to providing an inclusive environment for everyone, regardless of gender, identity, and expression. Basically, keep things short, be polite, and people will be polite to you. So yeah, just a short form of that. And you can connect with Melbourne Python on our socials as well to keep updated with everything that's going on. What you saw earlier was the Slack, for instance, which is the main group for the meetup where we deliver messages and all that. So on the web, we have a presence as well on LinkedIn, which you can find us by Melbourne Python user group, or you can also match us as well by Mastodon from @melpy@mastodon.social. And for the agenda for today, we'll have Cersei starting off with introductions, which we're currently doing right now. After that, we'll have our first speaker, Owen Elliott, who's right over there. And we'll pretty much be talking about useful and not so useful introspection in Python. After that, we'll have a bit of a break for more food and drinks. And we'll have a quick announcement as well from Nick on behalf of PyCon 2024. After that, we'll have Kai talking about optimizing SciPy's RGI module with Cython. And after that, we'll just close off and continue networking and close the doors at 8 p.m. And of course, all this can't have happened without our great sponsors, Judo Bank for providing us this great venue and providing us the great food, alongside AWS as well, who's rewarding us with a great pizza, and of course, JDP, who is helping us as well, providing stickers and also the drinks. And as I mentioned before, we are mostly active on Slack, so we have a lot of conversations going on Slack pretty much. So you can find different channels on Slack. There's announcements, generals, jobs as well for people to post jobs or pretty much for find jobs as well. We also have random volunteers. Essentially, if you want to stay connected with everything, stay connected with the different channels, feel free to scan that QR code. I'll pretty much be putting that up again at the end, or anyone who fails to be able to get into that with the QR code can also just come up to me as well, and I'll help you get scanned into during either the break or after this meetup concludes. And of course, we always are open to these three things. So if you want to speak at a meetup, please do get in touch with me, or you can also get in touch with me or Kai, and you can also look at the meetup page as well. We often post a specific forum too. I also often post a forum as well on our Slack, so you can pretty much just put in your topic there, and we'll get back to you for being able to speak at meetup. And for sponsors, if you're interested in sponsoring, do feel free to, same as well, reach out to me or Kai, and we'll talk to you through it. We're always happy to be able to get support for the meetup. And finally, also volunteering. A lot of the meetup is run from volunteers. We all here, the main organizers as well, we run it as well on a voluntary basis. So do feel free as well to reach out to us too if you would like to volunteer your time as well. We have a lot of different things that you can also volunteer in, including helping with social media or helping out with the running of the event too. So if you're interested in that, feel free to reach out to me as well, or Kai, either at the break right at this event or just after the event as well. So yeah, that's pretty much for me. And that's really the end of the introductions. So without further ado, I'd like to now pass over to our first speaker, Owen. So while Owen sets up, I'll just introduce Owen. So Owen is a solutions architect with experience in AI implementations spanning a variety of domains. He currently works at Marco, helping customers build multi-model vector search and recommendation systems.
Hello, hello. Perfect. Great. Thanks for having me along and coming along to listen to the talk today. So what I want to talk about is introspection in Python. So I think there'll be a lot of things in here that probably many of you are familiar with, but I'm hoping that I can make Python do at least one strange thing that someone here hasn't seen before. So for the things that I want to talk through, we'll start with a bit of an introduction to introspection for anyone who's not familiar with the concept of introspection. We'll go through some basic examples and use cases for introspection, so control flow and debugging is a couple of classic ones. We'll do some less useful things with introspection as well. We'll look at some of the inner workings of Python through inspecting some objects at runtime. And I'll also talk about how I applied introspection to solve a real-world problem that we were having at Marco to do with processing data at scale. So introspection is basically the idea of being able to reason about properties of objects at runtime in a program. So this sort of differs to where you might reason about the data of an object typically, is my value greater than or less than this? Instead we're looking, does this object exhibit this property? Does it subclass this other attribute? We're looking at these properties of the objects rather than the data. It's often considered a subset of reflection, which is something else that people might have heard of, which is where a program can also then modify attributes of these objects and modify its own code at runtime as well. Typical use cases, control flow is a really common one. I imagine a lot of people here have used introspection on types and attributes, knowingly or unknowingly, to modify the control flow of their program. It's very useful in error handling and debugging as well. Not all languages support introspection, but Python supports it very, very well. There's a lot of reasons for this, and we'll talk about some of those as well as we go. And just a note on some of the examples today, there's lots of ways that you can design the software. Introspection is not necessarily the only solution to a lot of the problems. They're kind of toy examples, but I wanted to talk through a lot of examples with actual code today to sort of demonstrate it in practice. So why is Python so good for introspection? Well, Python's an interpreted language, so we have lines of code being passed to the interpreter and compiled as they come, so we can grab this information at runtime about objects really, really easily. It's dynamically typed, so we have no type safety around what we pass into objects, so it needs to have this information to be able to decide whether it can or can't do something with a particular object as it runs. Part of that is this concept of duck typing, which we'll talk about as well. There's a lot of built-ins in Python which have great support for introspection out of the box, so we'll run through some of those examples. And there's also some great standard libraries in Python as well. So the inspect library, for example, dis, which lets you view disassembly of your code, and AST, which lets you actually pass abstract syntax trees of your program at runtime. The other thing with Python is it's got very, very permissive scopes. So there's not really anything preventing you from accessing pieces of information about objects as your code runs. So Python comes with a lot of things out of the box to support introspection. So in this example here, we have a basic object for a person and some introspections that you might be able to apply to it. So we can check whether it's an instance of something, we can check whether we subclass something, and everything subclasses object, of course. We can check whether we have attributes, we can list what the attributes that are assigned to that object are, we can list their attributes and their values as well with vars. We can get the type of the object, and we can also even introspect things like the docstring for the object as well via help, because docstrings are also interpreted as part of your code in Python. Introspection is really, really powerful in the context of control flow. So we have a super simple example here, which is being able to define a common interface for averaging color channels in an image, where we can accept either a numpy array or an image, and we can check the type of our input at runtime and apply any necessary conversions so that it's compatible with the later operations in the function. The control flow, using introspection for control flow, lets you leverage behavior based on different data types, and it also lets you extend this concept of duck typing in Python. You can write very flexible and well-organized code using these sorts of patterns. So the concept of duck typing in Python is this idea where if it walks like a duck and it quacks like a duck, then it must be a duck. In the case of an actual Python object, we can say if it is iterable with iter and next, then it must be an iterable object. And that's the reason why you can do for loops on sets or lists or dictionaries or anything that exhibits these two dunder methods. I know something I run into a lot is trying to serialize objects which look like they should be simple to serialize but are not known to libraries like JSON out of the box. Example here being that JSON only knows about a certain set of primitives in Python, so int, float, bool, string, dict, list, and tuple out of the box. But what we have here is a couple of iterable things that look like iterables, so we might as well treat them as iterables. So we can write a function recursively to convert any dictionary which has values which are iterable in nature into something that we can then serialize. So in the case that our data is dictionary, we can go and make all of the values serializable. But in the case where we have an attribute that exhibits this property iter, which lets it be iterable, and the type is not one of the primitives that we already are aware how to convert with iter, then we can make that serializable by using a list comprehension. Another use case for introspection is this is applications in debugging as well. And there's a lot of nice things that you can do here as a developer. So I'm sure everyone's stuck plenty of print statements within their code before while trying to work out what's going on. But we can print some pretty interesting information about our objects as our code runs by applying introspection. It lets us poke around both in our own libraries and also within the libraries of others that we might be relying upon, because again, there's no protections around scope in Python, it's all public. We can also use it to do things like trace code paths, work out where we came from when we got to this point that had an error. So this example actually stems from a question that I got asked at work by one of our software engineers, which was in Marco, we instantiate the client canonically as MQ is the variable name that we use for it. And so we had an error to do with, I think it was with CUDA, and the question was, in the error message, should we say, use mq.index, or should we use, client.index? But a user might not necessarily be aware of the objects that they're accessing, they might just know it by the name, copying it from the documentation. So the question was, can you actually work out what somebody named their own variable in their own code and give them a custom error message based off the code that they were using? So in this case, we use the inspect library in Python, and that lets us actually grab the current scope and the execution frame that the program's up to. Because we'll be calling this function from another function and we want to get that parent's function, we can take the current frame and do 2 steps backwards from there. In that frame, we can then grab all the local variables that were defined. So this will be in the caller's scope from the function that's calling this function. We can then look through all of the objects that are in that scope, finding through the items in that scope and try and find the one that is the one that I am, and then return that. What that looks like in practice is if we have a function here which checks whether or not you've provided an int to the add1 function, we can actually raise an error and use that to grab the name in the caller scope. So where I've called my variable string var, we'll see the type error we actually get back from Python is actually aware of what I've written in my code. And we can use that for error messages, but we can also use this concept for debugging as well, where you might have multiple sources that call to a function and you want to work out at runtime which one called it. You might not necessarily want to raise an exception, you might just want to print it out as a debug statement. There's lots of sorts of use cases for this. The other part of what I want to talk about today is some of the, I'm calling them less useful applications, although I then did go and find some uses for them, so I don't know if it's quite so well titled anymore. But there's a lot of weird stuff in Python, and introspection tools in Python give us a really interesting way to actually get in and sort of analyze some of these behaviors. So I'm sure everyone has seen dunder methods before, so also known as magic methods, and these are methods that you define on a class that give you special behaviours with a lot of the built-in functions in Python. So things like repr, which lets you print, add, which lets you use the plus operator, iter and next, which I've talked about already for looping, and get item for element access. There's an endless list of all these dunders, and yet obviously being the most common one for defining how to instantiate an instance of a class that we define. Now, underscores in Python are kind of a little bit special. So a single leading underscore is typically used to indicate that a variable should be considered private within that scope. Obviously, as I said before, there's no actual true privacy or public scopes in Python, but we can indicate to other developers that, maybe you shouldn't go messing around with this variable because we want to consider it to be private. So we'll put an underscore in front of it. But it doesn't really provide you any actual safety, as you can see in the example here. We can still check whether we have an instance, where we have that attribute associated with our instance of the class. We can also directly access it from the class. Where it gets weird is when we add 2 leading underscores to our variable. So in this instance, we add a third one, the try to access me, and we define a getter for it as well. And what we'll see is that while our getter works, our direct access to that variable raises an attribute error saying that it doesn't exist upon that class. And our IDE thinks everything's fine, and it all looks good, but we fail at runtime. So if we create an instance of our class to actually have a look at what's going on, we can use the dir, which lets you print out all the attributes assigned with the class. And we'll see down the bottom, we've got some of the things we defined, the value shouldn't access, the get method, and the value you can access. But the first thing that we've got that comes up is this one that we didn't define, and this is called name mangling in Python. So whenever you do a double underscore in front of a variable, Python will actually mangle the name by inserting underscore and using the name of the class that you put in front of it to basically change it at runtime without really telling you. Mangled variables are still accessible though, once you know the name of it. The naming is deterministic, so they don't provide any true private, but they give you this illusion of a private scope. So you can still access it directly once you know the name, and that naming is done deterministically as well. So I guess just some notes on using double underscores. It's not really very often recommended. The main use case for it is where you have a class, a subclass is another class, and they can use the same name prefixed with a double underscore because they'll be mangled to different names when the program actually runs, and so they won't conflict with each other. But in my experience, it's a pretty limited scope of applications where that really is genuinely the best solution for the problem you have at hand. There's a lot more dunders in Python, so using dir in a fresh interpreter there, we can actually just print all of the things that exist within that scope that we're currently in. And so we'll see a few sort of common ones that we'll be familiar with, like name, which is the reason that we have to do if name is main when we're running a main file in Python. We'll see built-ins as well, which is actually a list of all the built-in functions that are available in the interpreter. A few other bits and pieces there, but the interesting looking one is our annotations dunder. So I think everyone should be familiar with type hints in Python. So in Python, you can provide type hints and they don't change the functionality of the program. They don't provide any type safety or actual type checking, but they're really useful for other developers to work out, what you were going on about when you wrote that function, what types you expected people to give to it, and help, IDEs with autocomplete and linting and all those sorts of things as well. What gets a bit interesting is if we actually print our annotations object out, which is a dictionary, we can see that we have our variable name num and we have its type int that we gave it. But what's interesting about the type int is that it's not actually a string representation of the type we assigned it. It's actually a completely instantiated instance of the type that we provided as the hint for that object. So what that means is that type hints are actually executable in Python. So type hints are objects, and you can use functions or instantiate classes or do all sorts of strange things within the hints itself. That's because everything is an object in Python, even your type hints. So we can do some really peculiar things with this. So in the first example here, we can actually infer the order of operations that occurs. So we have num, and we assign it to 5, and we type into it with a piece of code that actually then goes and removes num from the global namespace of Python. We don't get any errors when we do that, but then when we try and access num, we'll see that it's not actually defined anymore because we've popped it from the global namespace. We can also use literals as types as well, so things like 3 or a string. That's why you may see when you want to type a class with its own name, you can put the name in quotes and use that as the type as a common pattern, because it's just actually a string literal as far as Python's concerned. We can also use singletons as well, so there are 4 singletons in Python: none, true, false, and the ellipses object. The ellipses object is a really weird thing in its own right. I think the only library I know of with a serious usage is NumPy, which uses it for part of its slicing syntax. But the singleton objects are basically 4 objects which exist only once in memory, and everyone else just references them. An interesting thing is this is actually relied upon by a bunch of libraries. So anyone who's used FastAPI may be familiar with its dependency injection system, where you actually use the dependencies within the type hints for your routes that you define. It's worth reading through the code. It uses the inspect library, and it actually goes through and it looks at all your type hints, and it grabs the function which you've passed into the depends and executes that to inject the dependencies when you call that API route. So now I'll talk about pulling it all together into a sort of real-world problem that I faced at Marco, and trying to use as many of these introspection properties and techniques that we've talked about so far as possible. So at Marco, we make a vector search engine. That's kind of our main product, but the other thing we do a lot of is fine-tuning AI models, so particularly focus on clip models for retrieval. So these are models that take an image and text, embed them into a common space, and then you can use that for search or other applications down the line, clustering and things as well. Obviously, being image and text models, they take quite a lot of data. We get data from our clients, and it's often client-specific or use case-specific. Anyone who's done a lot of data wrangling knows that you can try and write a lot of generic functions, and it'll get you most of the way, but when you're starting to deal with specific use cases and clients, you will end up writing some amount of custom code every time you go and do this data wrangling. The real key bit is how do we work out what our arguments are and how we can batch them and how we can analyze them. So to do this, I use the inspect library. So we grab the full argspec for the function, which is basically all the information around the typing and the function definition itself. So in this case, the arguments and the annotations that we have for them. We can then loop through all of our annotations, all arguments in the function, and grab their annotations. And what we want to know is we want to find the first argument that is either annotated as a list, as in the Python primitive list, or has the attribute origin, which is exhibited on the typing library, so the capital L list used in typing, and check that that origin is also list. And that will be the argument that we'll use for batching. You can also specify batched args separately if you don't want the implicit behavior of selecting the first. We then can convert all of our arguments into keyword arguments, because in Python, positional arguments can also be specified as keyword arguments, which is a nice property. So we'll convert them all into keyword arguments, and then we'll create batches based off the batching argument that we decided with that previous piece of introspection. And that's how we can get a set of batched arguments that we can then distribute later. So then what I want to do is extend this, because specifying those reductions is a little bit painful and a little bit tedious. So we also wrote an auto-parallelize version, which lets you instead type into the function the reductions that you could feasibly apply to that function's output. So the nice thing about this is it's still no functional code change to the code that you've written already. We're just using a change to the type hints, and the way these type hints are set up, they should function the same way in your IDE as if you typed it as list int with the autocompletes. So how do we do? Oh yeah, you can do other. We've got other reductions as well. So like a counting example here. So if you can count across keys and then reduce those by summing all the same keys in all the dictionaries that it returns, you can do. There's a bunch of different reductions that are implemented into it. So this goes back to some of the weirdness with type hints being objects and being executable. What we can actually do is we can define a base class, and then we can subclass that and also subclass the type that we want all of the type hints from, so list and generic. And then we can actually stash our reduction function within the type hint itself. So then when we get to calling auto-parallelize in the function, we can do additional bits of introspection to grab the argspec from the function. We can grab the return type from that annotation, and then we can check whether or not our return type subclass is the reducible base class, and if so, then we know it must have the reduction attribute on it. We can grab our reduction function from there. So it's all tucked into the type hint nicely. And yeah, the result of that is that with a one-line change, so I guess, yeah, squaring a bunch of numbers here, we just wrap our function call in auto-parallelize, and we can get a nice speed up to our execution time. So the original single-threaded execution. The nice thing about using multiprocessing is this works well with CPU and IO-bound tasks as opposed to threading, which is typically best only for IO-bound. So 4-second speed up on that dummy function there. But yeah, we sort of apply this to downloading images and yeah, modifying files and doing a lot of that batch processing work. So yeah, recently for a fine-tuning job, I think we pulled down about 35 million images. We were able to get about 4,000 images a second by parallelizing it with this. So I also put together some recommended resources which are worth checking out if you found any of the stuff in this talk interesting. So I also have another library called Contemplation, which is sort of a bunch of different introspection tools. It has some of the code I showed earlier for that, getting the names in different scopes from functions. It also has some, you can give it an object and it will determine the type hint for that object at runtime as well, so there's a few interesting things you can do. There's another interesting library here, multi-method, which is a Python library that lets you overload functions in Python, and it does that by setting up dispatches based on the type hints you assign into the function. There's another really good one here. It's more of an intellectual exercise than anything you should use seriously, but Fuckit is a library that suppresses all errors from your Python code. It's pretty fascinating. You can use it to wrap imports of libraries. You can use it as a context. You can use it as a decorator. It actually modifies the abstract syntax tree of your program at runtime to remove errors from it, which is pretty wild. And obviously it breaks your code in the process entirely, but you won't get any errors. And another really good one where I actually learned about the executable nature of type hints that is worth checking out is 5 Horrifying Techniques to Get You Fired, which is a great talk from Andrew Hill at the University of Warwick. Awesome, thank you very much.
Thanks, Owen. So we have about 8 minutes for questions, if anyone has a question.
That was a great talk, Owen. Went into a lot of really interesting things. So I'm just wondering, you listed a bunch of patterns. Are there any anti-patterns that you would recommend avoiding when mucking around with Python internals?
Yeah, that's a good one. I have to think of any great ones off the top of my head. There is, as with anything you do, I guess, there is like some execution overhead to doing introspection. I think the most recent version of Python made some big improvements to the efficiency of the inspect library in particular. But if I would probably recommend avoiding it in like highly performance critical parts of the code. So you're doing it outside of your loop to determine how best to do things within the loop is that's fine. But inspecting say every 40 million objects within a loop, you'll get an execution overhead for doing that. So yeah, thinking about where you place it in your code is definitely something to consider. Another weird side effect, I guess, of the type hints being executable as well is if you put something in a type hint that actually takes time to run, then using that function will take additional time to run because that type hint will actually get executed when you use it. So that's sort of a weird gotcha, I guess.
for questions.
Thanks a lot for the talk. I guess my question is, when you do inspection with multiprocessing or multithreading, is there any kind of weird conflicts, like looking at a frame in a process or that sort of edge cases?
Yeah, I guess if you do the using the current frame from a multiprocessing, so yeah, when you do multiprocessing in Python, the multiprocessing library, it operates a little bit differently on each operating system. So on Linux it uses fork under the hood, on Windows it does something slightly different. It's not something I've actually played around with too much, but there might be potentially some, I think the ultimate result is that you get basically a fresh Python interpreter in each process, but I mean there is some weirdness around multiprocessing in general where, to use the library that I wrote, you do need to make sure that the processes that it spins up don't then try and execute the multiprocessing code that you use to spawn it again as well. So it has to be wrapped in something like a main function, otherwise it will get executed from its children processes and then it will immediately crash. So there's definitely some stuff to watch out for there. In terms of the introspections itself, it's not something that I can think of where there'd be any particularly weird behaviour, but it's also not something that I've explored in great detail.
Right, if there's no more questions, then again, let's give Owen a round of applause. All right, also, we're gonna take a quick break now, and yeah, we're gonna pretty much take a quick break for about 15 minutes, as mentioned in schedule, and yeah, feel free to get some more pizza, get some more drinks, and yeah, we'll regroup here in 15 more minutes. Thanks all. Hello again, everyone. Great to have everyone back again, and hope you've managed to get a good break, and also some drinks as well, some refreshments as well after our first session. So now we're gonna go into, before we go into the second session, I'd just like to hand over to Nick to talk a bit about PyCon 2024. Over to you, Nick.
Hello. Hi, I'm Nick. I'm the sponsorship coordinator for PyCon AU 2024. PyCon AU 2024 is being held in Melbourne in November. So November the 22nd through the 26th, it says on the website. And essentially PyCon AU is the sort of the predominant conference for PyCon developers and Python enthusiasts in Australia, kind of as the name goes. So our call for proposals or call for papers is currently open. We're looking for people who have spoken at Python conferences before, people who have spoken at other tech conferences before, and also people who have never spoken at any conferences before. We are absolutely keen to hear what you have to say. We are open to mentoring people who've never done a proposal for a conference before. All you have to do is reach out to us and let us know, and we'll help you develop an idea that you've got into something that's a really great proposal for our conference. And hopefully we can turn that into a talk at PyCon AU 2024. The other thing we're doing at the moment is looking for sponsors. So if you work somewhere that is looking for Python engineers, if you work somewhere that wants to sell something to Python engineers, if you work somewhere that would see this as a really great professional development opportunity for your existing engineering staff, sponsorship is a really great way of connecting your organization to the Python community, not just in Melbourne or not just in Sydney, but across Australia and also the region. We've got a bunch of people who come across from New Zealand, we've got people who come in from around the APAC region just to come to PyCon AU because they know as a conference it's really strong technically, but also one of the most welcoming and inclusive conferences basically in the tech space in Australia. So if you would like to have your organisation or your company support PyCon AU, if you reach out to sponsor@pycon.org.au, you'll get me. If you come and have a chat after Kai's presentation, you'll also get me in a much more direct way. So please consider sponsoring the con. If sponsoring PyCon is not for you, absolutely please do consider proposing a talk. The call for proposals ends on Sunday, July 21st. We use an anywhere in the world model. So long as it is Sunday, July 21st, somewhere, your talk will still be, or you can still propose your talk. I think that's pretty much it from me. Thank you very much for having me. Please be in touch if you've got anything you'd like to say.
Thanks, Nick. So now I'd like to welcome Kai to give our second talk for tonight. So while Kai is setting up, just want to give a quick introduction to Kai. So Kai is the software and data engineer at PHP and maintainer of SciPy. He has been programming in Python since 2009 and enjoys pushing the language to its limits. And he's also the co-organizer as well of this Melbourne Python meetup. So without further ado, Kai, over to you.
Yeah, hello everyone. So this is Inside SciPy, Optimizing Scientific Python, which is basically a case study of how we optimized the module inside of SciPy. So who am I? Like, why listen to me? I have a degree in maths. As Rinaldi's already said, I'm a software developer at PHP. I'm also a SciPy maintainer. So this is work that I did that other people are now using. And I really, really don't like slow code. So that's my reason for doing this, basically. So what are we actually going to do here? We're going to try and talk about how I approach optimizing slow code. So it's Python, it will be relatively slow. This is one of the techniques I have in my toolbox to make it faster, and I think other people would like to know about it too. This is using SciPy's regular grid interpolator as an example. We'll get into what a regular grid interpolator is in a second. And this work was done mid to late 2022. So it's a little bit outdated now. We have done more work since then, but this is a good case study. It's a nice self-contained project. Yeah. And some topics include benchmarking, profiling, extending Python with native languages, and code optimization in general. So just a couple of disclaimers before I start. This is not entirely my own work. So I did have help. It's a collaborative project. Other people helped out. And this is the abridged version. So there was a lot of profiling, there's a lot of trial and error to try and get it to what it was. So with that, there's some thanks here. And I don't know why it's doing that. So firstly, thanks to Vegnu, who was the co-contributor on this. So he was the person who actually knew what a regular grid interpolator was before I started optimizing it. So he helped with a lot of the algorithmic side of things. And we had a couple of reviewers as well. So what is linear interpolation? So given a pair of points, we want to estimate a value between them. We do this by basically drawing a line between them, a straight line, and saying we're at this point on this line, so we must be near this value in the y-plane. That's a very, very simplified version. There's a lot more to it, but that's the short answer. So why do we want to do this? Because, well, gathering data can be expensive. So if you're doing clinical trials, it takes a lot of money and effort to get a data point. So people might want to interpolate the data from those clinical trials to actually get a result. Okay, next slide. So what's special about SciPy's linear interpolator is that this can be done in n dimensions. Well, technically up to 64 dimensions. So it uses NumPy array under the hood, but if you're doing it in more than 64 dimensions, you're looking at some other specialized module anyway. And SciPy's regular grid interpolator works on rectilinear grids. That basically just means it's a rectangular grid underneath it. And this avoids the expensive triangulation step, which takes a long time in other libraries with you doing it naively. So this is an example of how we would use it. So we've got import NumPy, import SciPy. We make 2 to the power of 14 points, which is 16,384, I think, top of my head. And then we just set up a grid with random numbers, so 16,000 by 16,000 grid with random points and interpolate those points. Now we make mesh grid, which just sets up points on the grid. We train our interpolator with method linear here. So that's the magic, and then we call the interpolator on our grid. Did that skip a slide? No. So, how do we figure out if it's slow? Well, the first trick is to benchmark it. So benchmarking is basically taking a measurement to see if the performance is acceptable or at what level the performance is. Benchmarking can get very, very complicated. There's a lot of statistics, there's a lot of understanding of how a process works to get an accurate benchmark. I'm going to kind of skip over all of that in this talk because this is about the optimization side, not the benchmarking side. And SciPy has its own benchmarking suite, which is based on airspeed velocity. And all of my benchworks are conducted on my computer with a pretty baby CPU. But what's important is that they're all on the same CPU with the same system. And I didn't try to do anything confusing like that. So this is an example of the benchmark I wrote. So we've got a timeout at 5 minutes just in case something goes wrong. We've got a setup from before. We basically run the same code as before. And then we time it below. So we just call the time below. So this is basically converting the example I had before into a benchmark. And this gives us 36.8 seconds. Now, is this fast? So the question depends on your use case. If you're going to leave it running overnight, that's not a problem. If you want to do real-time interpolation of some data on a mine site or get feedback on a clinical trial or something very, very quickly, that's a problem. SciPy has a second function for linear interpolation. This is interp2d, which is a wrapper for feedback. It's written in Fortran, and it's very, very fast, but it only works at 2 dimensions. So let's compare the two and look at their performance. So here I've compared both the setup time and the call time of the regular grid interpolator and the interp2d for our 2D problem. And we can see that interp2d, the call time, is much, much quicker than the regular grid interpolator call time. So we're basically comparing this value here to this line here. So for a library like SciPy, which is very, very considerate about performance, that's basically unacceptable. So we need to do something about it. So where do we find the slowest points in our program? Well, this is called profiling. So profile is a set of statistics about how your program performs. It's useful as we can focus our attention on the slowest parts of the code, because that's the parts where we'll have the most impact. And here we'll use Python's inbuilt C profile. There are many, many other profiling tools, but I'm assuming that most people will be familiar with C profile. And this is the output we get. So note here, firstly in the top left, you can see that it took 63 seconds, which is much, much slower than our 36 seconds. So profiling adds overhead. What we can also see is that the top 2 lines here took by far the most time. So that's where we're going to optimize our code, because that's where we get the biggest impact. So what are these two functions? First one is find indices. So this finds the edges between which 2 points are located, and it calculates the lowest normalized distance to the lower edge. So with regular grid interpolator, we basically take a cube, unit cube, we go between all the points, and we interpolate on that unit cube. And here's the code of that function. I'll give everyone a couple of seconds to overlook. Okay, cool. So the next part is evaluate linear. This calculates a linear interpolation on the unit cube. So before we found the distances, now we're actually calculating the interpolation on it. So we can see that it uses broadcasting extensively and sums each point within a weight depending on the distance to that point. So I'll give everyone a couple of seconds again to look over that. Keep in mind, this is an optimization-based talk, not an interpolation-based talk, so this is just background. So you don't need to understand the code, it's just a bit of context. So what can we do about it? Well, there's a couple of things we should consider. Firstly, there's algorithmic complexity. So can we use a better algorithm to optimize our code? In this case, the answer is no, not really. So interpolation takes 2 to the n, big O of 2 to the n operations, which is going to be slow, especially when it's done in pure Python. We can also talk about our data structures. So we can use NumPy arrays, which are much more efficient data structures versus lists and tuples. And we should consider that it's pure Python. So being pure Python adds a lot of computational overhead to our computations. We need to check the data type every time. We need to have inefficient accesses to our data every time. And it's just, we're wasting a lot of time and space and effort. So we could remove this overhead by doing the computations in a more computationally efficient language than Python. So how do we extend Python? Turns out this isn't the first time somebody's done it. There are a lot of ways of doing this. I've listed some of them here. So the first is Fortran and F2Py. This is what we have in Interp2D. At SciPy, we're trying to move away from Fortran as a backend language just because we can't maintain it as well as we can with C. Like the skills just aren't there for people willing to do it on their free time. We can do a manual C or C++ extension module. This is probably the most performant, but also the most maintenance. Like with any software project, we're trying to reduce the maintenance of what we're doing. So we decided not to go down that route just yet. There's Number. So Number is a just-in-time compiler for Python. It actually uses a lot of introspection as well, so maybe you can use some of what you learned there. But it is a very good tool. The problem is it does it at runtime, which adds an overhead as well, which we don't want. Then there is Python. So Python is a ahead-of-time compiler for scientific Python. It's very good, but we don't have the experience with it just yet. So I didn't have the experience with it to start working with it on a large project like SciPy. And then there's Cython. So what is Cython? Cython compiles a superset of Python to C. It supports optional static type declarations. So you can just say something is a list of integers, which will map to a list of integers in memory. It allows for very fast program execution. So when written properly, it's basically the same speed as C. It keeps up the high program productivity, and it usually uses the .pix file extension. So what happens if we naively Cythonize it? So Cython can be run on any .py file, and it will work. It'll get the same result. It generates a C file with Python bindings for you. So what happens if we move evaluate linear and find indices to a .pix file and compile it? Well, it gets significantly slower. So I've personally never seen this before, that Cython generates a slower file even when it's compiled ahead of time. So just to give some context, Instagram managed to get a 3 times speed up on their Django routing engine just by running through Cython without making any code changes. So seeing it be, 10 seconds slower is pretty disappointing. I've never actually seen this before, so it is unusual. I don't really understand why, but I've got a couple of hypotheses. So firstly, there's some overhead converting Python types to C types, and this can be significant, especially if you're using a lot of Python types like lists, tuples. The compiler can't optimize it well without static typing. So we've basically just told Cython that here's a list of Pi objects. But Cython knows what a Pi object is, but it knows nothing about it. So it doesn't know if it's an integer or a float or a custom class. It can be anything. It has to check at runtime every time. And if you do that in C or do that in Python, it doesn't really make a difference. And there's heavy use of Python-specific functions, such as itertool, zip, and so on. Cython can't optimize these, so it's still interacting with the Python interpreter. So how can we investigate how much it interacts with the Cython interpreter? So as I've said before, Cython compiles everything to C. This does not mean it avoids the Python interpreter, and the Python interpreter is usually slow. Now we can compile Cython with an annotate flag, which gives us a nice HTML output of the generated code and where it interacts with Cython. And the Cython interactions are highlighted in yellow. So as a rule of thumb, yellow is bad. And that's a lot of yellow. So I've done this for both functions. They're about the same, so they're just as bad as each other. So, we can see indices, we've made a list, we've told it nothing about the list, so it has to interact with the Python interpreter. We've got zip, we've got untyped things. Yeah, it's not great for performance, basically. So what can we do about it? Here are a couple of techniques that we used, and I'll show you the output of code at the end, but I'll go over the techniques first. So, use memory views. So in Python, like I've said, everything's an object. And every object contains a pointer to the heap, which contains the actual data. A list of numbers is a list of pointers to numbers on the heap, which is very, very slow. Memory views are basically a C array with a little bit of wrapper, but basically a C array. This is much, much more performant than a Python list. We can add some static typing. So here I've got an example of the find indices function, which I can demonstrate. So we've got a couple of things here. So we've got the grid from before. We've told Cython it's a tuple, and we've told it it's not none. So it doesn't have to check if it's a none value. Now we've got our xi's here, which is a 2-dimensional array, right? So we've got this double, so we're telling it it's a 2-dimensional array of doubles, and we've made a memory view, so there's the 2 columns here, which say that it's like the 2-dimensional array. We've also added types to all of our variables. So we've got long, double array, and so on. And Cython has types for all C types. So that's ints, floats, pointers, everything. We can also remove Python-specific functions. So this is things like zip, list comprehensions, itertools, functions. We can also remove some NumPy functions. So say, for example, numpy.where and numpy.search sorted are implemented in Python, which is very difficult to optimize again. And here is the interesting part of the inner loop, rewritten to be more Cython friendly. And this gives us a pretty significant speed up. We can even go further than this. So compiler directives are instructions that affect the behavior of Cython code. By default, Cython code will act more like Python than C. They can be used to further speed up the behavior of the code, but you make a trade-off between being Pythonic. whatever that means, but that can be another question. So here, for example, we've used for. So we've used wraparound. So that means that you can't use negative indexing on lists or any iterable really. We've used bounds check, which means that if you access an out of bounds element, it'll just crash. We've used C division, so there's some undefined behavior there. And we've used initialize check. We haven't used initialize checks. So we can just pass garbage memory into our functions, which obviously isn't great, but we've just assumed that the user is responsible with our function. Big doubt there, but yeah. And this leads to another speed up. So it's not as significant as adding the types and all that stuff, but it does shave another 2.5 seconds off, which is not ignorable. So what are the consequences of this? We've sped up the benchmark by a factor of 2. That's a little bit disappointing. So this is on the lower end of what you see with Cython. So we can normally see 10, 100 time speed ups if we're doing it efficiently. But that's because we've only optimized the 2 inner functions. So what we're doing now is calling Python code, converting it to C, converting it back to Python code, converting it to C again, doing the computation again, and then converting it back to Python code. That is a lot of waste, and we're working on improving that. It also hints at large Python interaction. So we're doing a lot of interaction with the Python interpreter, which we can probably get rid of, but haven't done yet. And we've added a compilation step to the project. So SciPy is already a compiled project, so it doesn't make a difference, but that may matter for your project. And we've made the code much less Pythonic. So it's written much more like C than it is like Python. Now this work isn't done. So we're looking for contributors, we're looking for people to help out. If you're interested in this kind of stuff, have a look at the SciPy Git repo, there's good first issue tags. Yeah, get involved. Thank you.
Thanks, Kai. Do we have any questions for Kai?
How much faster was the Fortran code? It looked like it was only a 2 times improvement, wasn't it?
It was quite a bit more than 2 times.
Okay.
So I can go back to the slide. So if we get there. There we go. So the Fortran call time is about a second, and the RGI is about 16.
Oh, okay.
Yeah, so the Fortran code is faster because it's optimized for 2 dimensions, whereas the regular grid interpolator works for basically anything that NumPy supports, which is up to 64 dimensions. And then there is a lot of overhead with converting back and forth to Python to C.
So is this the point where you'll be like, okay, well, we've hit that target?
No.
How far do you keep improving?
Basically as long as somebody wants to work on it. So we have sped it up. So this was end of 2022. We have sped it up quite significantly since then as well. So we're still not at interp 2D level, but we are getting there. Yeah.
How much of NumPy is written in Python and therefore slow?
Too much. So NumPy dispatches to Fortran or to BLAS and MKL, I think, or to a BLAS implementation. But a lot of the wrappers around that are still written in Python. So best case scenario, you're not actually calling the type directly, you're calling a dictionary which maps to the function, and then call the function. Did that answer? Yep.
Did you have a question? Yeah, sure. I'd just like to say that common theme between the two
chats is that if you're going to look at performance metrics, make sure you benchmark so you can actually gauge success.
Yeah, great talk. I was just wondering, have you spent any time benchmarking how the memory allocation impacts the performance of this particular function?
Not directly.
Okay.
So we've got a very similar benchmark to that. We're trying to avoid the memory allocation entirely because, well, we still need to do it, but we've got one big memory allocation at the top, and then we just use that.
Okay.
Yeah. So we have tried to reduce it. We haven't benchmarked it as well as we should have.
I mean, the reason I ask is some time ago, I wrote a library that basically handed off an array-like interface to the underlying M map in the system, because I ran into a problem where that allocation was the bottleneck on the equipment that we were using, but it had a lot of that kind of like back and forth that it seems like there was there.
Yeah.
But yeah, I was just curious.
Yeah. So we're actually in the process of looking at rewriting it in C++ entirely, but that's a lot of work. That's a big commitment. So yeah.
Just with the Cython thing, I noticed that it doesn't support Python typings, because I noticed the actual way that they were defined were the opposite from Python typings. I wonder if it picks that up. Is it smart enough? If your code in Python has that, is it going to be able to pick that up?
It does now.
Yeah.
I don't like using it that way because I'm old-fashioned and something.
Yeah.
But yeah, so it will use typings. It will use its own types though. So you need to give a typing to Cython.int or Cython.double or whatever. That's just because it uses C types rather than Python types. So like what an int is in Python is ambiguous to Cython because it could be like a character, it could be a int, it could be a long.
Yeah. And the other thing I was going to ask, just because you mentioned you're going to rewrite it all in C++, as someone who's written C++ modules for Python, it's very, very, a lot of boilerplate, very, very finicky. Have you considered Rust? Because it's the Py03. No, some people have. There was someone who did a talk on it back here a few months back, and it's actually, there's a library in Python called Py03, and it has amazing integration with Python, and it handles all of the boilerplate for you. You just sort of like annotate it, and it generates all the modules, it generates all of the lookup tables and everything that it normally needs.
So Cython does that as well.
Yeah.
So you can define a wrapper for a C class or a C++ class.
Yeah.
The answer to your actual question is yes, I have considered it. I would really like to do it, but we need some evidence of how it's going to work and how it's going to affect it, because it is downloaded a lot, it is used a lot, it affects a lot of people.
Yeah.
So
You don't want to become the second cryptography.
it's a lot of questions.
Hi, thanks for the talk. Does using Cython complicate distributing SciPy?
Yes. Well, so you need to either provide a compiled module for each target, so like Windows, Mac, Linux, PowerPC, whatever, or you need to provide a C file which they can compile themselves. But then they need a C compiler, they need, stuff goes wrong when you ask people to compile their own projects. Yeah.
Do we have any more questions on the floor? Beautiful. If not, let's give Kai a round of applause again. All right, so we've reached the end of the event. As usual, just gonna give another quick highlight as well of these three things. So again, we're always looking for speakers for instance, for our next month meetup as well. So if you're interested in speaking, please do reach out to me, reach out to Kai. Happy to talk you through it. And if you're interested in senior sponsoring volunteering, please do so as well. We're always looking for volunteers especially, so we're always happy to talk through it, get you geared up, and yeah, pretty much like what to expect as well. In particular, right now we're looking for those who can help out with logistics on the event day itself, for instance like this, and we're also looking for someone who would like to help us manage our social media presence as well. So if you're interested in that, please feel free to reach out to me or Kai, and happy to take you through it. But again, just want to navigate back to this. If you haven't had the chance to also join the Slack, again, just want to remind everyone this is where everything takes place. So happy to pretty much, if you haven't had the chance, please do scan it, and you will be in the loop for pretty much our next discussions. Can reach out to us directly this way easier too, since we are on Slack. And yeah, that's really about it. I think that's about it. But again, thank you again so much for coming. And I think we still have just a bit of time. So yeah, feel free to mingle a bit more. But yeah, pretty much aside from that, we're gonna close off the event and shut the doors at 8. Thank you all.